In this lecture, we will look at a design example of a telescopic op-amp. So we will assume that the MOSFET process parameters are given to us. So let us first list them down. So the MOSFET parameters that are given are mu and Cox is 60 microamp per volt square. And mu P Cox is 30 microamp per volt square, and VTN is equal to VTP is 0.7 volts, and we'll assume that lambda n is 0.1 volt inverse, lambda p is 0.2 volt inverse, and we will assume that L min, the minimum length for N and P type transistors, is 0.5 microns, and lambda is specified for L min. And finally, we'll assume that the power supply is 3 volts. Now these are the device parameters. Now we come to the specifications of the op-amp. So the op-amp specifications are as follows. So we will say that we want the DC gain to be at least 3000. We will say that the total power dissipation is 10 milliwatts, and we will say that the output swing, peak to peak swing, is required to be 1.5 volts. So these are the specifications that we will start off with. This will be more of a basic design rather than having the frequency parameters, frequency response of the op-amp. We will first do the basic design of the op-amp. Now the first question would be where we should start. So of course, always a good place to start is to set the bias currents through the transistors. So we will say that the current, so we will say we'll start off with the power budget. And we will say that op-amp core uses 3 milliamps, and the other 330 microamps will be used for biasing. What I mean is that 330 microamps is going to be used to generate VB0 and VB5 and VB3. So of course you will need to use some kind of reference current source and maybe a bunch of current mirrors to generate these kinds of voltages. I will not go into the details of how to generate these, because these have been seen before. These have been seen before when we had looked at single transistor circuits and current mirrors. So let us assume that this is known. So we will assume that, and we will not do that part now. Now let us look at the op-amp core. So if the op-amp core uses 3 milliamps, so M1 to M8 has bias current of 1.5 milliamperes each. So that's the first thing to realize. This current would be equally used as half on each side of the op-amp. So this is a good way to start, because now we have fixed the bias current. We now need to fix the width and the length of the transistor based on the specifications. So the next step what we will do is to look at the output swing. So the output swing is going to tell us what the VD sat of each transistor is going to be. So let us assume the cascodes are biased such that you have maximum swing possible in the circuits. So in which case the output voltage can swing up by a certain amount and swing down by a certain amount. We will also make some common sense assumptions. So we will assume that the output, when the op-amp is placed in feedback, the output is biased at VDD over 2, which is 1.5 volts through DC feedback. This is a fairly common sense assumption, because you are making sure that the op-amp can swing up and down around this VDD by 2 value. Once you do that, since we want a swing of 0.75 volts above 1.5 and 0.75 volts below 1.5, as you can see, you have M8 and M6 above, going to VDD, and M4, M2 and M0 going to ground. So you can see that if the output were biased at 1.5 volts and it needs to swing to 0.75 volts, so that on either side, so that the overall peak to peak swing is 1.5 volts, then you will find that the supply, between supply and ground, you have an additional 0.75 volts at the top and bottom to make up the full 3 volt headroom. So now we need to allocate this 0.75 volts on either side to the appropriate transistors. So let us now start. So we can see that when you go look at the upper side, you need to ensure that M8 and M6 have enough headroom. Therefore you can say that so the overdrive voltages, so let us say the VSD sat of M6 plus VSD sat of M8 plus VSD sat of 8 has to be equal to 0.75 volts. Similarly, on the lower end, we can say that the VDS sat of 4 plus 2 plus 0 should be equal to 4 plus 2 plus 0 should be equal to 0.75 volts. Now you need to make a design decision. So let us first, to make our design easier, we will assume that M1 to M4 are identical. This will reduce our search space. The design can be refined later based on signal considerations. We will say M1 to M4 are identical and M5 to M8 are identical again. So that gives us just a pair of GMs and GDSs to design for. So in which case, once we make this clear, since they have the same widths and lengths and the same bias current, they will have the same VD sats as well as the same GMs and GDSs. So the next step is to point out so that VSD sat of 5 to 8 should now be 375 millivolts, and VDS sat of 1 to 4 should be equal to 250 millivolts. Now let us start with the signal portion of the circuit, and let us say that we want to calculate the GM of the input pair. So we will write down the GM expression for the input pair as follows. So this is nothing but 2ID1 over VDS sat of 1 to 4, and this is 3 milliamps over 250 millivolts. So therefore the GMs of the input devices is 12 millisiemens. Now what do we do next? We can also write down the expression for the GDS of 1 to 4. GDS of 1 to 4 is nothing but lambda n times IB of 1 to 4. So this is nothing but 0.15 millisiemens, and this means that RDS 1 to 4 is equal to 6.67 kilo ohms. So now we are in a position to figure out what the requirement on the output resistance is. So let us do the same thing for the upper transistors also, so that we get an idea of the PMOS resistances also. So if you look at the PMOS resistances, so we will do the same thing. GM 5 to 8 is equal to 2ID 5 to 8 over VSD 5 to 8. So this tells us that the GM of 5 to 8 is 8 millisiemens. Similarly, GDS of 5 to 8 is lambda P times ID of 5 to 8, and this is 0.3 millisiemens. This means that RDS 5 to 8 is of the PMOS transistors is 3.33 kilo ohms. As you can see, the PMOS transistors have a lower GM as well as a lower RDS. So now that we have the cascode transistors, we should also figure out the intrinsic gains of the devices, so that we can look at the output resistance of the overall op-amp. So GM by GDS of transistors 1 to 4 is equal to 80, and GM by GDS of 5 to 8 is equal to 26.67. As you can see, the intrinsic gain of the PMOS transistors is much smaller. This is because we have apportioned higher VGS minus VT for the PMOS transistors, which means they should have a smaller size, and for the same current they will have a smaller GM. And because the lambda of the PMOS is larger than the lambda of the NMOS, it turns out that the GDSs are larger for the same bias current and the RDS is smaller. Therefore, what you are seeing is for these particular set of device parameters and the particular design we are looking at, the intrinsic gain of the NMOS transistor is much larger than that of the PMOS transistor. Now, based on this, we will now say that the impedance looking upwards, which is, I'll denote by R up, and the impedance looking down, I'll denote by R down. So we can write the overall output resistance R out is R up parallel R down. And what is R down? R down is GM into GM 1 to 4 into RDS squared 1 to 4, and this particular value ends up being equal to 533.6 kilo ohms. Similarly, R up is GM 5 to 8 times RDS squared 5 to 8, and this number ends up being 88.8 kilo ohms. Now there are a few things we should note. The first thing we should note is that the up and down resistance are fairly one-sided, so that is something we should note. So the up resistance is much smaller than the down resistance. So this means that the actual effective DC gain of the op-amp is more or less going to be limited by R up, and in many designs you do not want it to be skewed in this manner, because then the impedance looking down does not contribute to the so in other words, the intrinsic gain on one side is much larger than the other, and therefore the effective gain you can extract out of the circuit is much smaller than what you expected. So if you were to look at R out is R up parallel R down, and that value ends up being 76.1 kilo ohms. Now we are now in a position to calculate the DC gain. The DC gain magnitude is GM1 times R out, and this number ends up being approximately 913. This is clearly too low for our design. We are expecting a gain of around 3000. So now what do we do? So we can do several things. The first thing we will look at is what is the DC gain, what is the R out that is required to reach a DC gain of 3000. So let us look at that. Let us look at the inverse problem. So the R out required is equal to DC is equal to 3000 over 3000 over 12 millisiemens. This is approximately 250 kilo ohms. Now the reason we are going this path is because the difference between the required DC gain and the DC gain we have achieved is so large that it seems like our original design, our original expectation is quite different from what we are getting, right? What we need. So therefore we are going to try a different approach. So now let us try this, let us compare this required R out 250 kilo ohms with the numbers we have seen. As you can see, if R up was equal to R down, so in other words, if R up equals R down equals 533.6 kilo ohms, if both of these were 533.6 kilo ohms, you can see that R out is approximately 250 kilo ohms. In fact, it's slightly larger than 250 kilo ohms. So in fact, now our job is clear. We should actually be trying to increase R up such that it is almost equal to R down. So let us look at how we can do that. So we need to increase R up, R down. So now we will take the opposite approach. So we will say, let us make it exactly equal to R down. What does that mean for us? So we want R up equals R down. The easiest way of achieving this is to make GM of transistors 5 to 8 equal to GM of transistors 1 to 4 and make GDS of 5 to 8 equal to GDS of transistors 1 to 4. If you achieve this, you can rest assured that R up will also be equal to 533.6 kilo ohms. So let us now ensure that this happens. So if we were to do this, then what we are saying is that we want R up GMs of the PMOS transistors to also be equal to 12 millisiemens, and we want the GDSs to also be equal to 0.3 millisiemens. We want the GDS to also be 0.15 millisiemens. If we ensure this, then GM 5 to 8 by GDS 5 to 8 will also be equal to 80, and this means that R up will become equal to 533 kilo ohms. So this is again a design constraint that we are going to apply. Now our final job is to figure out whether this will actually meet our design requirements. So first of all, the first step is to see how you make GM 5 to 8 equal to GM 1 to 4. So this means, since they have the same bias current, the W over L ratio of 5 to 8 should be equal to the W over L ratio of 1 to 4. So this is easy to achieve. You choose the width such that the width to length ratio such that they are equal. Now what about the second condition? This is a little bit harder to achieve because fundamentally the two devices have a different lambda. So the first step is to try to achieve a larger output resistance. So what we'll point out, we know from basic device physics that lambda is proportional to the inverse of the length of the device. Okay. So now what this means is that we want if you want larger RDS, so this means smaller lambda, and this means longer L. So now our job is clear. We need to increase the length of the PMOS transistors such that they have a smaller lambda and you get a larger RDS. How much do we need to increase the length? Now that is given by the ratio of lambda p over lambda n. So lambda p was 0.2 volt inverse for L equals 0.5 microns. So now, since we wanted to double the resistance, so let us look at RDS of 5 to 8 and 3 to 4. You can see that there is a factor of 2 separating these two. So we want lambda of the PMOS to also be equal to lambda of the NMOS so that you get the same RDS. To do that, since and we know that since we know that lambda n is 0.1 volt inverse for this, so this tells us make the length of the PMOS transistors to be equal to 1 micron, so that the new lambda, I'll call that lambda prime, is 0.1 volt inverse. And once you do this, once you set the length of 5 to 8 transistors, 5 to 8 which are the PMOS transistors, to be equal to 1 micron, the lambdas will now be 0.1 volt inverse, and we can calculate the new RDS prime for 5 to 8 will be equal to lambda p prime times ID 5 to 8, and this will also be equal to 6.67 kilo ohms. Now the next step is to set the GMs to be equal. We have now said that GM of 5 to 6 to 8. A small correction here. This is true. There is a small correction here. Please note that this is not correct. This should be in the ratio of the mu n C ox. I'll make that correction separately. Into the ratio of mu n C ox over mu p C ox. Please note this correction. I have erroneously said that the width over length ratio of 5 to 8 will be equal to width over length of 1 to 4. They should actually be in the ratio of the mu n C oxes. In our case, so this tells us that so W over L of 5 to 8 should be 2 times W over L of 1 to 4. This is the width to length ratio. Now we can calculate the value of width to length ratio for 1 to 4 from the value of the GM of the device. So let us do that. So we will start from the basic GM equation. 2 mu n C ox W over L times ID 1 to 4, and this tells us that the width to length ratio for transistors 1 to 4 should be equal to 800. So this tells us that they should be 400 micron over 0.5 micron. This is because we had chosen the length of the transistors to be 0.5 microns. This means that W over L of transistors 5 to 8 should be 2 times 400 by micron, 2 times 800, so which is 1600. So this is nothing but 1600 micron over 1 micron, because we had chosen the length of these devices to be 1 micron. Finally, we have to go back and calculate the VD sats of the devices, because now we have changed the sizes of the devices. So if you go back and calculate the VD sats of the devices, so VD sat of devices 1 to 4 is equal to 0.25 volts, as we have set this, and this gives us a VGS 1 to 4 of 0.95 volts. Now this VGS and VDSAT number, these numbers will be used to set the values of VB3 and VB5 and VB0. Now what about VSD-SAT of 5 to 8? So it turns out that since everything, both GM and current values have been set to be equal, so this is also 0.25 volts, and it turns out that this is less than the required value for the swing, which was 0.375 volts. So therefore, output swing limits are okay. So now this particular design will meet all specifications required from the original OpAmp. So the final requirement is to set the values of VB3 and VB5. I will leave that as a homework exercise. I just wanted to point out, we have still not decided the size of M0. So one easy way to set the value of M0 is to say that M0 has 0.25 volts VDSAT and twice the current as M1 to 4. So it is meant to have the same VDSAT due to the swing limits that we have imposed, and it carries twice the bias current. Therefore, you can say that M0, so you can set the width to length ratio of M0 to be twice the width to length ratio of transistors 1 to 4, and this is nothing but 800 microns over 0.5 microns. So this completes our design.